Alright guys, welcome back. This is the third and final part of this force method problem. If you're watching now, I'm going to assume that you've seen the first two parts of this video. If not, there will be links in the description to the YouTube video. But otherwise, we just spent a very long time doing the force method. Basically, we started with this 2-degree statically indeterminate beam. We did superposition, then we did a whole bunch of moment area method stuff, all this. Carry on, it took us a very long time to work through. Eventually we found some reactions, and then we were left with basically solve, or what we had finished off with in the last video is we had solved all of the reactions. We got MA, AXAY, BY, and CY. Now the only thing we want to do now is just draw the shear force diagram and bending moment diagram to wrap up this problem. So if we draw a free body diagram of the very left hand side, taking a virtual cut infinitesimally close to A, we know that we got that reaction here, AY pressing up, which is 19.6 kilonewtons. That means the internal shear right at that point has to be 19.6 going down. And this matches our positive sign convention where for beams and bending we have the shears looking like that and the moments looking like that. So we got shear pressing down on the right of virtual cut, which means we're starting at positive 19.6 kilonewtons of shear in this region here. So let's start here. Maybe let's use a straight line. That'll probably look a lot nicer. It's going to kick us out uninterrupted right until we hit this point load. So we're starting at 19.6 kilonewtons. And then once we hit this point load, this is going to drop us down 50 kilonewtons. So 19.6 minus 50, it's going to bring us down to 30.4. Let's label this on 30.4 kilonewtons. All right, now this is going to go straight over uninterrupted until we hit the reaction BY, which is going to kick us up 90.2 kilonewtons. So maybe what we should do is we'll label this on as negative 30.4. So negative 30.4 plus 90.2 brings us up to 59.8. So let's draw that on just like that. It's going to be somewhere up here. And we have 59.8 kilonewtons. And then the shear drops linearly by 10 kilonewtons per meter over the next distance of the next span of 10 meters. So basically 59.8 minus 100 is going to bring us down to negative 40.2. So it's going to drop nice and linearly to negative 40.2, which is going to be somewhere like down there, and then we can close this off just like that. So let's label this negative 40.2. And we're expecting that because the reaction here at CY is 40.2, and then we can kind of confirm that same thing if we just draw a little free body diagram, taking a virtual cut infinitesimally close but to the left of point C. We know that we have this reaction here of 40.2 kilonewtons going up, so that the shear here, the distributed load is going to be infinitesimally small if this distance x is infinitesimally small. So then all of the shear here right at the very end has to be 40.2 going down, and that's opposite the positive sign convention. So that means it's a negative shear of a magnitude of 40.2 right at the end. So it looks like we've done that correctly. All right, so the next thing that we're going to need to do is we should have labeled on, well actually, yeah, we got 5 meters here. We got 5 meters here for this distance. And then this distance here is not 5 because this triangle is not symmetrical, but with similar triangles, we can really easily find that this distance, the base of this triangle is just 5.98 meters. And then the base of this triangle is just going to be 4.02 meters. And then we want to take the area of each of these. So this area is just going to be base times height. So 19.6 times 5 meters is going to be 98. And then this area in here is just going to be 152. That's the negative. And then the area of this triangle, 1/2 base height, is just going to be 178.802. And then this area in here is going to be, we can label that on if we want as an A. And then this area down here is going to be a negative value. It's going to be negative 80.802. All right, and these units of the areas are all in kilonewton meters. So then when we come down to the bending moment diagram, we want to start off with the internal moment, but we already know what the internal moment is going to be. So if we come back to this, this is the free body diagram of point A, right? Just taking a virtual cut infinitesimally close to the right-hand side of A. So if we also add on the applied moment, or basically the reaction moment, it's acting on the beam in a counterclockwise sense, and that was for some reason I erased it here. It was 44 kilonewton meters from the previous videos. So this was 44 kilonewton meters. Now, if this distance in here, again, if this is infinitesimally small, then the force couple here, basically like the moment that it causes is negligible or tends to zero. So that means that we have an internal moment infinitesimally close to point A of 44 kilonewton meters going going clockwise on the right-hand side. And so when we have it going clockwise on the right-hand side, that's opposite the positive sign convention. So we're starting with a value of negative 44 kilonewton meters. So let's put it on about there, and we have negative 44. All right, so in between this region, basically in the first 5 meters, we have this horizontal line here, or constant shear. So it increases linearly by the magnitude of the shear force diagram, and it's increasing because this is a positive area. So we have negative 44 plus 98. That's going to bring us up to a value of positive 54, which should be somewhere right around there. So we have positive 54 kilonewton meters. Now as we traverse the next 5 meters, this is a negative area, so we've got to subtract. It is constant here, so we have linear change in the bending moment diagram. So basically we have 54 minus 152, and that is going to bring us down to negative 98, which would be somewhere like about there or something. All right, so we get negative 98 kilonewton meters for the internal bending moment right at point B. Now, in this next region, we have positive change because we have positive area, but because this is a linear section, we have actually parabolic curvature on the bending moment diagram. And if we put in a little marker here, basically up until this point is where we have positive change, and then the area of the shear force diagram becomes negative, and then we start getting negative change. Now, when we have negative 98 plus 178.802, that's going to bring us up to 80.802. And then the curvature is the same on the way back down because it's the same slope of this line, and 80.802 minus 80.802 brings us right back down to 0, and that is exactly what we would be expecting, basically due to the constraint, or not the constraint, like how the original problem was set up, which was right here, right? We would expect a 0 internal moment, basically, when we right at the roller reaction of a span like this. So there we go. We found the reactions, and then we just drew the shear force diagram and bending moment diagram of this original problem using the force method. Let's see if I can find where I had that. There we go. So we got the bending moment, or shear force diagram here. We got the bending moment diagram, and then we had all of the reactions. Now, I think if you have anything more than 1 degree indeterminate, the force method is a really slow and clumsy way to do it. You're better off using the slope deflection method or 3-moment equation. And I actually solved this exact same problem using those 2 different methods. And so I'll put links to those also in the description. But make sure you check those out as well, because I kind of think they're like a little bit better in most cases than using the force method for these like really long problems that are more than 1 degree statically indeterminate. So anyways, guys, if you made it through all 3 of these videos, then props to you, and I really hope this stuff helps, because yeah, it's definitely a beast using the force method. So thanks for watching, guys, and good luck using this stuff.